Hello, Agent Pi, this is the director. There is a message you have to pick up. We've been waiting for months to get it, so this mission must be perfect. Good luck!
Finally, Agent Pi got the message. Can you help me decode it? Well, in order to decipher any message, we need to use cryptography, which is the process of converting ordinary plain text into an intelligible text and vice versa, so that only those for whom it is intended can process it. For example, this technique is called the Caesar cipher, where each letter in this encrypted message represents the previous letter on the alphabet, so we would get this message. Is this a coincidence? No. In fact, cryptography relies heavily on mathematics. This message could be deciphered by anyone using frequency analysis, but when it comes to merging cryptography and math, we get an impenetrable shield.
To understand how powerful this shield is, let me show you the world of number theory, the branch of mathematics that deals with the properties of integers, like prime numbers. These VIP numbers are only divisible by themselves on 1. However, for two numbers to be called co-prime, their only common divisor has to be the number 1.
By the way, it's 1 p.m. or should we say 13 hours?
To address this question, we need modular arithmetic. Let's say we continue counting from 12 on this clock. Visually, we can associate 13 to 1, 14 to 2, and so on. This is because our clock has 12 positions, and on this scale, 13 and 1 represent the same spot. Therefore, this can be mathematically written as this. Now, with this knowledge, for two coprime integers, x and n, Euler came up with one of the biggest pillars of cryptography nowadays. In this formula, the Euler's phi function denotes the number of smaller coprime integers to n and satisfies the following properties.
This is all we need, ladies and gentlemen, to present the RSA algorithm.
Imagine Tom wants to send a secret message to Mike. Tom will save it on this box and will lock it to ensure that only Mike, who has the right key, can have access to the box. Here is how Tom and Mike create their lock and key. First, they choose two secret prime numbers. In real life, they need to be thousands of digits long, as the basis of RSA is factoring extremely large prime numbers, which is currently a non-deterministic polynomial time problem. In other words, an incredibly hard problem to solve, even for the most advanced computers. By multiplying them, they get a number n, and now after finding phi of n, the next step is choosing a number e, such that it's in between 1 and phi of n, and it's coprime to n and phi of n. Finally, a number d is chosen such that e times d modulus phi of n equals 1. It's time to test the lock and the key.
Tom wants to send this message to Mike, so he assigns the value of 4 for practical reasons. Tom encrypts the message using the lock this way, which equals 2 and can be assigned to b. This is what Tom will send to Mike. Now Mike has to decrypt the message by following the exact same steps but using the key. And look at the result. It's 4, the original message.
Cryptography has huge applications. Banking cards, computer passwords, cryptocurrency, and many more. But once again, it's math who saves the day. Oh, Agent Pi, I have a new mission for you.
On my way, sir.